my friends at MakePath have graciously agreed to join us today. I'm very excited to have them. And they're going to give us a tour of some options and things for you all to know about. So Brendan, would you give a little introduction of yourself and a little bit about MakePath? We're really fortunate to have you. Brendan is one of the founders of MakePath, so it's a great honor to have him here.
Yeah, thanks, Jenna. So like Jenna said, I'm one of the co-founders of MakePath with Pablo Fuentes. And MakePath is an open source spatial data science company based in Austin, Texas. We have a heavy focus on Python, and we work with various clients, both in GIS and outside of GIS, to help with data science solutions that are heavily focused on open source. One of the first items I wanted to show the group was an infographic that we put together of a history of open source GIS tools. Over the past 40 years, there have been a really rich set of tools developed in the open source community to specifically address geospatial problems. And we know that, spatial is special in a lot of the challenges that come with dealing with spatial data, both raster and vector. So we put together a infographic which shows some of these projects and then also highlights the folks that were involved in the project, a little bit of its history, so you can learn more about a specific project. In this presentation, I'm going to be going deeper into some of the tools that we're passionate about, and also wanted to show you guys how to connect these tools into existing platforms like ArcGIS Pro and ArcGIS Desktop. We take the position that open source tools augment your toolbox. It's not a dichotomy between using proprietary tools or open source tools. We find that they complement each other nicely, and at MakePath we use both ArcGIS and QGIS along with open source tools and proprietary tools of various sorts. But in this presentation, we're going to highlight a lot of the open source tools that we're particularly passionate about. If you want to learn more about MakePath, I'd urge you to go to the MakePath blog. That's makepath.com/blog. And you can see some of the projects and work that we're promoting and new events. There's a recap from our latest 𝐀𝐫𝐢𝐳𝐧𝐚 annual conference in Dallas, which was great. And just wanted to take a moment to just thank AGIC and Jenna and the group for giving us this platform to talk about tools that we're passionate about and hopefully recruit some open source developers at the same time, or at least contributors and testers. So thank you guys for attending. I'm started primarily as a GIS analyst at the Nature Conservancy in about 2007. I started building open source tools in niches that I felt like where there was gaps in the open source ecosystem or in the proprietary ecosystem. This is my GitHub page right here, and it has shows some of the projects that I'm particularly excited about. Xarray Spatial is a raster-based spatial analytics package for Python, and I'm going to be looking at some of the available offerings there, but then also talking about the wider Python ecosystem. And I got involved in Python because of ArcGIS. When I saw that Python was integrated into, I think it was like maybe the ArcGIS 8.x series and that era of ArcGIS, it made me really want to learn more about this scripting language to avoid the prior scripting languages of, say, like VBA or Avenue or some of the other scripting languages that were integrated into ArcGIS. When I dove deeper into Python, I found a much larger ecosystem that I could pull ideas from that may be adjacent to Geo but have an impact in Geo. And we're going to look at some of those findings through the lens of projects like Xarray Spatial. So Python was a language developed to teach programming to children. So it's very approachable and has a nice syntax and is particularly concise in how you structure the code. So it's an easy language to get going with, and most folks start by scripting repetitive tasks, like say opening zip files or setting symbology on your layers in ArcGIS, and you will see a Python console right within ArcGIS Desktop. And that Python console gives you power into your whole map document and also interfacing with data structures through ArcPy. I would assume that some folks are familiar with ArcPy here. ArcPy is the Python package that's integrated into ArcGIS. and is a good starting place for seeing the power of Python, even if you're still working solely within the ArcGIS stack. But in the documentation for ArcGIS, you'll see that there's a page on installing ArcPy. And you'll notice as you scroll down that there's this tool called Conda. And they ask you to open up the Python command prompt and then install ArcPy using Conda. And Conda is one of those connecting pieces that gives you a hook into installing third-party Python packages into your ArcGIS Python distribution. And this is a really good place to start. So like if you currently have an ArcGIS set up on your machine, a lot of the tools that I'm going to be showing today are installable via Conda. So following kind of just the ArcGIS documentation, you can stub out ArcPy here for something like Xarray Spatial, which is one of the libraries that I'm going to be showing. So this is a hook within ArcGIS that you can tie in these additional open source packages and augment your toolbox with different either domain specific libraries like hydrosheds for watershed modeling, or other tools like maybe Flask or Django, which are for building web servers in Python. But they can all be integrated into your existing Conda environments in ArcGIS. So just want to highlight that for the ArcGIS users, that this isn't a dichotomy between like throw ArcGIS away and only use open source. All these tools can integrate together and can augment each other. And Esri as a company is one of the leaders in open source in both open sourcing the file geodatabase specification and other things like their geometry libraries. And so they've been a leader in promoting open source and showing the power of user maintained and contributed libraries. So just wanted to highlight that. So Conda, this hook inside of the ArcGIS documentation, Conda is an open source package manager that will allow you to install third-party packages. So you can look at code on GitHub, or you can find some tools from our open source history infographic and then install them via Conda. So in looking at tools, they break down right into both raster and vector. That's at least the frame that I want to talk about these tools in. They're the major areas of data that we're concerned with in geospatial. And a tool that we're working on and continue to grow is called Xarray Spatial. And this is akin, by analogy, you would think of this as a lot like the spatial analyst toolbox inside of Esri products. So this is looking specifically at doing raster-based analytics. And if you scroll down in the documentation, you'll find instructions for installing this using Conda. Xarray Spatial, areas where you can grab example notebooks which show implementations of using the tools with sample data sets. And then you'll also see our feature matrix, which is covering the different areas of raster analytics that we support within Xarray Spatial. So under classification, we have things like classic 1D binning methods that we all know and love, like equal interval and natural breaks, but this is applied to rasters. So this is binning raster values. Quantile, a generic reclassified. And as we look through this feature matrix of available tools, you'll notice that the different columns apply to specific areas that we're supporting for Xarray Spatial. So the first column on the left here supports NumPy arrays, and we're going to talk about NumPy arrays and this data array which wraps NumPy arrays and their importance within the Python ecosystem. Dask arrays allow us to scale this operation to larger than memory data sets that either exist on one machine or many machines. So if we want a cluster of computers to coordinate on a specific task, we can use a Dask array. So say we're dealing with all of Landsat and we want to address all of Landsat at once, but we want to use, say, 10 Amazon machines to run a multispectral analysis, say like NDVI on Landsat, then the Dask array would support that. So we can support scaling horizontally to many machines. The CuPy column in GPU indicates whether or not this tool is available for NVIDIA CUDA-enabled GPUs. So that's using modern hardware to gain performance on spatial operations. And depending on the operation that you're doing or how you chain them together, a GPU may be a good option. It might not be if it's you know, there are some gotchas with GPUs, and we can go deeper into those. And then the fourth column here on the right is showing those tools that are available on multi-GPU systems. So if we're going to coordinate multiple GPUs on a single operation, like doing a reclassify, whether that tool is currently available. We're trying to finish this feature matrix, and every week, you know, we have a new checkbox somewhere in this matrix of what applies. So in the functional areas of raster analytics, we think of classification, neighborhood analysis or focal analysis, and looking at hotspot tools and being able to look at focal statistics, multispectral analysis and combining multiple bands together to pull out detail. And we have the many flavors of band math that you can do here, and they're well supported because they're fairly easy to implement in element-wise on rasters. So you should recognize some of these like NDVI, but then there's other flavors of NDVI and other layers that you can pull out from multispectral imagery. Some basic pathfinding, proximity tools like proximity allocation, direction, and proximity. So these are generating distance grids on top of rasters. We currently support those for NumPy and Dask, but not yet for GPUs. We also have raster to vectors. So this is polygonized. So taking your raster and pulling out those contiguous blocks of values into a vector file. Classic surface tools like hillshade and aspect, slope, viewshed, and we'll look some more at viewshed. And then zonal tools, which tend to be extremely used. So out of all the modules, I think zonal is probably used the most in doing zonal statistics, and also cross-tabulate, which would be equivalent to, say, tabulate area in looking at the breakdown of classes in a given zone. So, but since we've developed these tools from the ground up, we have different interfaces to zonal statistics, which you may find interesting as we look at some examples. There's also local tools, but they don't come in that often, and we'll probably deprecate these tools at some point. There's Xarray Spatial exists within an ecosystem of tools, right? As we scale out to multiple machines or we use GPUs, we're relying on certain open source dependencies to be able to do that. And this graph shows some of those tools and their relationships. And this can serve as a little bit of a guide through the ecosystem. So if maybe Xarray Spatial isn't a tool of interest, maybe one of the dependencies is, like something like GeoPandas or Dask, or you can see the relationship to GDAL if we're familiar with these really foundational open source geo tools like GDAL and GEOS for vector and GDAL for raster. But one of the foundational libraries for scientific computing in Python is NumPy. I just want to quickly define what NumPy is. So NumPy gives us two things. It gives us a multi-dimensional array object in Python, so we can represent a 2, 3, or 4D raster in memory in Python, all defined as a single data type, which makes computation on top of NumPy arrays fast. While Python itself, if you were, say, working on lists, is actually a fairly slow language. NumPy gives us the ability to write performant code while staying within Python. So NumPy is one of those foundational libraries, and you see that in ArcPy with functions like raster to NumPy and NumPy to raster. That within ArcPy, it's identified that NumPy is one of those key integration pieces to allow the open source tools to play nicely with things like ArcGIS grid files or mosaic datasets. So NumPy is a great area of learning. The second part of NumPy, right, are a set of universal functions on top of those multi-dimensional array objects. So things like being able to do a sum or a min or a max and have it understand the dimensionality of your data. So this is NumPy. Unfortunately, NumPy can be a little arcane to read the code for, especially if like you wrote some NumPy code a couple weeks ago and then are going back to it. You're referring to, like, say, individual elements in your raster as integer indices, and that can be difficult to read in the future. That's where this library called Xarray came around. And what 𝐀𝐫𝐢𝐳 gives us is the ability to put labels on the dimensions of our NumPy arrays. So no longer are we thinking about integers in a large array. We're thinking in labels, like things like soil or elevation or land cover classes. Those are the labels that we can apply to our axes of our arrays. So 𝐀𝐫𝐳 is the library that we based ℕ spatial on because of that that nice user experience of having labeled arrays, and it also implements the netcdf memory model. So if folks are familiar with the common file formats like netcdf, then ℕ will be very natural to work with. So this is a little bit from the fire hose. We're gonna, send out a link of everything that we're saying here. So don't feel you need to write everything down, but I did want to highlight a library called Numba, which allows us to implement geospatial algorithms within Python while still having the performance of NumPy. So as we look at some code inside of ℕ spatial, we'll see that it's using Numba to gain what we call the vertical scaling to make our algorithms faster by using this open source JIT compiler. So what we essentially do at makepath as we're working on ℕ spatial and other tools is we use Numba to implement geospatial algorithms and then provide those interfaces to users so that they're easy for anyone to use. But if you wanted to extend these libraries yourself, Numba would be a good library to look at. If you want to get up to speed on using a tool like Numba, then ℕ spatial is a good example implementation for how you would deal with some geospatial edge cases and issues that come up. So Numba is a vertical scaling technology that will allow you to implement algorithms in a performant way from Python. This would be just to contrast the use of Numba to, say, the use of GDAL, right? So GDAL, foundational geospatial raster analytics library implemented in the C, C++ ecosystem. What Python tends to do is wrap that C and C++ code, which makes it easy to interface for Python users, but difficult for those users to extend. So if you wanted to extend GDAL, you would need to then context switch over to that language and really the history and culture of the GDAL project to extend that project. At makepath, we wanted to create a library that was easily extendable by analysts while staying within the Python language, and that's what Numba gives us. To scale operations to larger than memory datasets, every year there's statistics published on the amount of new data created, and it's going up rapidly. Being able to coordinate multiple machines on a single problem is valuable. So here, using a project like Dask, so Dask would be analogous to, say, Apache Spark, if you're familiar with Apache Spark, which is for distributed computing. Dask gives us distributed computing within Python and also has some nice features and companion libraries for dealing with geospatial data. One of those would be Dask GeoPandas, and we're going to talk a little bit about GeoPandas, but Dask is a great library, not specifically geospatial, but does have some abstractions like the Dask array, which will allow you to coordinate multiple NumPy arrays while still writing sequential code. So as you're writing, say, an analysis script, you can refer to a Dask array, which under the hood has pieces of memory on various computers. So everybody at your office could get together, set up a Dask cluster, and then use each other's laptops to process a big geospatial job. And that's what Dask gives us. And that's why we integrated this into ℕ spatial, was to be able to gain horizontal scaling, or scaling to multiple machines, multiple processors, multiple threads. That's what Dask gives us. And we take Dask and we add the geospatial context to it. So I've talked a lot about rasters, but I wanted to talk about some other open source projects that pertain to attribute data and also to vector data. Pandas is a library that came out of the finance domain. So these were Wall Street traders that came up with Pandas. And Pandas gives us the equivalent of an Excel worksheet, but within Python. So we have a data structure which inherently understands rows and columns and allows you to do those aggregations and reductions, like doing the max of a specific column or doing joins between attribute tables. That's the area of pandas. And fortunately, some folks came around and added spatial support for GeoPandas. And that adds the Geo series, or the equivalent of the shape field, right? But to the GeoPandas geo data frame. So as we're at makepath, as we're working with vector data, we tend to represent it as GeoPandas geo data frames. So we're talking vector here, and we're able to do the attribute manipulation from pandas. So all the things like joins and reductions and pivot tables, but with a geospatial context with GeoPandas. This is on the open source history infographic and is one of those really great libraries out there. To be able to scale to GPUs, we want to be able to use modern hardware to accelerate geospatial operations, and we're using 𝐀𝐫𝐢 to do that. So 𝐀𝐫𝐢 gives you a NumPy compatible API or interface, but on top of a CUDA-enabled GPU. So there's some operations which are computationally intensive that can benefit from use of a GPU, and that's where 𝐀𝐫𝐢 comes in. That's really the third column on the feature matrix that I showed from X-Array Spatial, and it addresses specifically working on GPUs. So if you're looking for examples of how to implement geospatial algorithms on GPUs, then X-Array Spatial would be a good place to go steal some code for or mine for ideas. Data Shader is another tool which is really interesting because it bridges vector and raster data. So Data Shader is a general purpose rasterization pipeline that allows you to go from vector representation to raster representation, right? So we're moving from coordinate lists of coordinates to regular grids, right? Just in the definitions of vectors and rasters in the geospatial context. So this is a really nice library. It was put together by Anaconda, the same folks that made Conda, and allows you to do intelligent aggregation of vector data that deals with problems like oversaturation and overplotting. So here we're looking at the continental United States. We're plotting 1 point per person based on the 2010 census, and then rendering an image. And the striking thing about this image should be that you're able to resolve the Midwest cities without having New York, Houston, Los Angeles, Chicago pull the color map and skew all the colors. That's because this was done using a log stretched color ramp instead of a linear color ramp. Those are some of the features inside of Data Shader. We love Data Shader, and that allows us to go from vector to raster and plays very nicely with X-Array Spatial. So in getting started with X-Array Spatial, you can go to the GitHub page, and we'll post that and send that along if you didn't grab it as we went through. And you can grab the example notebooks that will lead you through sample data and how to use X-Array Spatial functions on top of it. So here we're procedurally generating some terrain using Perlin noise. We're doing some color mapping on top of that using a pseudo elevation color map, applying a hill shade, and a bunch of the surface tools are available in the surface notebook. With the proximity notebook, you can go deeper into the proximity tools on how proximity direction or proximity allocation work. And this is available, again, in the examples area of X-Array Spatial. And also the zonal tools. I think the zonal tools are awesome because in our zonal tools, you can specify any function you want to run on a zone. You don't just need to use sum, range, min, max, standard deviation, variance. Those are the ones that come with ArcGIS. In this version of zonal statistics, you can scale it to many machines. You can run it on very subtle expressed functions for each one of your zones. In this example, we're looking at transects across a fake terrain. So we're thinking about hiking. It might be hard to resolve the hike line here, but we're breaking down our hike across the terrain into different days. So this data frame that's returned is indexed by day, and we have some of the zonal stats we know and love, like just the summary stats. But then we can also show how we can apply custom functions and get the results for each zone also. So that's something that we really wanted, was the ability to express custom logic executed on each zone for our zonal tools. So we recently started a CUDA working group. This is specifically for supporting GPU implementations on X-ray spatial. And what we did was we looked at a couple of functions that we thought would be particularly great for the GPU. So terrain generation, view shed, and then ray tracing, or doing hill shades, and being able to cast real shadows across the terrain. So in the resulting result of our working group, here we have a little demo where what I'm doing in the demo is I'm clicking on a location to generate a view shed, or the line of sight between an observer and target pixels, while we're rotating a light source. This is all executing on a very small GPU that is able to keep the frame rate up in doing both dynamic hill shading and dynamic view shed on top of what is, Crater National Lake Park elevation DEM. Also wanted to highlight our work with the Planetary Computer. So the Planetary Computer is a new project from Microsoft, which is taking curated data sets, things like Landsat, Sentinel, and other data products, combining it with open source tools like X-Array Spatial, Rio X-Array, bokeh and data shader, and these libraries that I've shown here, with scalable compute on Azure. So what you get is a Jupyter notebook with connections to relevant data sets and open source tools to power the whole thing. So you can log in and have access to data and tools and be able to express your idea without getting stuck in the data munging part, or getting stuck in trying to install this third-party package that won't install on your system. So Planetary Computer is a project that we've been participating in supporting the open source tools that run on top of it. One just last thing, just for anyone who really wants to get down the code, if I wasn't technical enough in this presentation, this is an implementation of that hill shade that I showed. So if you're interested in seeing how we did the hill shade from the video with the light source, then you can look at hillshade.py. And what you'll see here is about 200 lines of code. There's a lot of documentation in here too, so probably a third of it's documentation, where we're able to cover doing hill shade on a single CPU, hill shade on multiple computers on multiple CPUs, and hill shade on GPUs and multiple GPUs. So this is less than 200 lines of Python code that from scratch implements hill shade for various platforms that's scalable to very large data sizes. So just wanted to highlight that for folks. If you're looking to either take examples of how to write code for GPUs or how to write code for CPUs, then this is a good place to look. And X-Ray Spatial in general has some nice examples of that. So thank you so much to AGIC, to Jenna, to everyone in the audience for checking us out. I feed my family on GitHub stars. So if folks want to come to makepath/X-Array Spatial and give us a star, that's always appreciated. But also I would love to hear from folks. You're welcome to reach out if you have any questions afterwards. I know we don't have too much more time now, but happy to take a question or two, or Jenna, just pass it back.
Thank you, Brendan. That was awesome, as usual, and a lot of really great information. My guess is that our folks are really going to want your slides and some additional reference material. If you are able to provide that, that would be super helpful. And we do have one question in the chat that I think we have time for. Does X-Ray or any of these tools perform spatial interpolation? Oh, you got muted.
Sorry about that. So there are separate interpolation modules for Python that do work on top of NumPy arrays and include all the different, cricking and everything that you could want in terms of interpolating fields. And that's so that is not within Xarray or Xarray Spatial right now, but I'm sure that there are other third-party packages that tie into the same data structures. One of the key parts of Xarray Spatial is that we introduce 0 new data structures. We're operating on existing standards from the ecosystem, not introducing new data structures into the ecosystem. So you could take a tool, say Data Shader, take the output and put it into Xarray Spatial, no problem. You could take the output from Xarray Spatial, put it into another interpolation tool that's part of the PyData or NumPy ecosystem, and you're good to go.
Awesome. That's great. And thank you. Just again, this is exactly what our folks were looking for. We've got lots of thank yous in the chat. I really appreciate your time today and look forward to the future. That's great.
Thank you, guys.